For our second test, test 2 here, just a little brief rundown of what we're covering for test 2. We covered chapter 2 for this particular unit here, specifically 2.1 through 2.5 and 2.7 is the current sections that we're covering. We started off with, in chapter 2 here, we started off with the definition of derivative. And as we learned, that process is sometimes, it's a little long, right? But it's important because, you know, derivative, we learned all those rules and sometimes we just forget what they really mean. So definition of derivative tells us really what it means. For f prime of x, the derivative by definition is the limit as h approaches 0, f of x plus h minus f of x over h. And what, again, just to review what that is, that's the thing we did in the first unit. This right here was that, here's our function. So we went x, at x, we're trying to find the derivative, which is the slope of that tangent line. And the way we found it is this right here, well, if we go out to x plus h there, then we've got this secant line, right? That's the slope of that secant line. And so what this says is if we let h come into 0, which means h is getting closer to 0, so we're coming into that x, what that does is that secant line slope matches the slope of the tangent line as we come in. And so that's what that is. That's our definition of derivative. It's the limit of those secant line slopes, which we did way back when we started that. And this, now we're calling it the derivative because that's an important thing. And again, it emphasizes that, yeah, this gives me the slope of that tangent line. And so that's what the derivative is. Now, for the test purposes, what I would tell you is, yeah, you will have to do some of these with the definition of derivative. Probably the first couple of problems that I have on the test, you're going to use that definition of derivative. And thereafter, it's the other rules that you have to do it. And, what you can run into, you got the, remember using the conjugate, factoring, other things. So a couple of them you'll have to use that definition of derivative. Just be aware of that. However, after section 2.1 and thereafter, maybe a little bit of 2.2 also, but thereafter we just use the rules. So let's just run those down. You got your power rule for derivative. You got your product rule. Quotient rule. And then we finished off with chain rule. And so yeah, multiple uses of those rules will be on the test. A couple of them, I think I specifically do a couple of problems that say use the product rule to do this derivative, use the quotient rule to do this derivative, use the chain rule to do this derivative. But several of them I don't tell you which rule to use, and so you have to be aware of which rule that you use. And like I've said before, that product rule, that's the toughest one to recognize sometimes because it's very easy to be going along, you're doing these derivatives, and you just come across f of x equals 3x squared cosine of x. Okay, well, it's very easy to say, that derivative is just derivative of that, 6x times the derivative of that. But what's wrong with that? Well, it's a product, and as we saw, on a product, you cannot do the derivative of the first times the derivative of the second. It just doesn't work out. that way. And so, yeah, it's 6x times cosine of x. Then I rotate that, if you will, and then do the 3x squared times the derivative of the cosine. So that's the toughest one sometimes to remember to do, is that product rule. I mean, quotient rule, that's fairly obvious when that happens. Chain rule, you got the parentheses and that sort of thing to help you remember to do that. Product rule, easiest one to. So be aware. Yeah, there'll be a couple where that product rule may sneak up on you. I won't tell you to use the product rule. Remember to though. Chain rule. The one thing I would mention is sometimes the chain rule isn't, again, as obvious. The one I'm thinking of is if you've got y equals sine to the fifth of x. Yeah, that one's not an obvious chain rule, because you don't have, chain rule, we're looking for that, what's inside, like, y equals cosine x squared plus 7, something like that. Yeah, that's a fairly obvious chain rule, because you got the inside and the outside, obviously, with the parentheses there. Clearly, you can see that, yeah, to do the derivative, I got to do the derivative of the outside, which is negative sine, with the inside staying the same. And then I got to multiply that by the derivative of the inside, which is 2x. This one, though, when I started with, sine to the fifth x, because of the way the notation has evolved here, it's not as obvious. But what I would do, what I suggest is, yeah, go ahead and write that with parentheses, which sine to the fifth x is sine of x to the fifth power. Sine of x parentheses to the fifth power. And then maybe it's a little more obvious. The inside is the sine of x, and the outside is the fifth power. So when we do our derivative, yeah, do the derivative of the outside, 5. Inside stays the same, fourth power, 1 less power. And then I do the derivative of the inside, which is cosine of x. And then you can write that however you please there. That's what I'd say on the chain rule. And then the other thing is, I like to call them, the other part of this test, applications of derivative. And what I would mention to you about that is, technically, I guess, it's not an application, but the derivative, by very definition, is the tangent, the slope of the tangent line. I like to call it an application because it is sort of that. So it asks for the slope of the tangent line. Now we know we call that derivative. We can find it with the derivative, which that means we can use all those rules to find it. And use it to find the equation of the tangent line. And then the other application is, not only is the derivative the slope of the tangent, but it's also can be considered the rate of change of the function. And again, some students struggle with the wording here, because I will probably ask you, if, say I've got the volume with respect to t is, whatever it is, 4t cubed minus 7t. I don't know. If that gives you the volume with respect to t of an object. What does v prime represent? I mean, it's obvious we can compute v prime, but what does, maybe let's, all right, so this is, what does v prime represent? It's one thing to be able to compute it, but what is it you found when you find the V prime? Well, that's where we use this terminology here. V prime doesn't give me the volume. This gives me the volume. So V prime doesn't give me the volume. What does it give me? The rate of change of the volume. At time t, or whatever t represent. So that's what I'm looking for. Give me that rate of change expression, okay? Or if it asks for the rate of change, that's what you're looking for. You're looking for the V prime. So, and of course, the other application specifically, we talked about velocity and acceleration. Well, velocity is just the rate of change of your position or height, right? Which means if your position or your height is s or whatever you call it, velocity is, so if this equals s, then the velocity is the rate of change of s, and so velocity is s prime. It's the first derivative, okay? And then if we do the application, the one application we did of higher derivatives is in the acceleration. Well, the acceleration is the rate of change of the velocity. It's how fast the velocity is changing. So, yeah, velocity is the rate of change of velocity. Acceleration is the rate of change of the velocity, and so it's the second derivative. Just do the derivative of the velocity. So those were specific ones. Think of anything else? Let me look. Oh, think of something else. The other thing that we did was interpret this with the derivative with the graph. So be aware of that. Yeah, if I've got a graph here, y equals f of x, and I want to compute, approximate f prime of 1, how would I do that? Well, f prime of 1 is, that's just going to be, it's the derivative at 1. Well, the derivative is the slope of the tangent, isn't it? And so what I would have in mind here is, yeah, come up to 1, draw in your tangent line, and then approximate that slope using the rise over the run of that tangent line. So the way I usually did it is, you know, run 1, and then what's the rise? Maybe I should have done, let me do it this way, a little less steep, so it's not as obvious. Well, yeah, if I do a run of 1, this one looks like it's a half rise, so just approximate it there. Something like that, just figure out the rise of the run, and that'll give you your derivative. Of course, you got to watch for, like if I did 3, it would be a negative derivative. Let's see, if I run 1, then it looks like it's a rise of -2, so f prime of 3 would be, I say -2 divided by 1, -2, something like that. And then, of course, the other thing is, if I wanted to sketch f prime here, I'd be able to do a whole graph of f prime. And remember, on those, what I'm looking for was just what I've got graphed here. If I sketch f prime, one thing I'm looking for is these horizontal tangents, because they will be, so it looks like at 1.5, I've got a horizontal tangent. Those will be 0 over there on the x-axis. In other words. And then you got positive slopes on this side, negative slopes on this side, so it goes from, this one pretty simple because it goes from positive, large positive to 0, and then starts getting bigger and bigger negative, so it just kind of turns into a line. What I've got graphed here. So be able to do that. Then of course you're looking for straight lines and corners. Well, that's the other thing. Derivatives. Where do derivatives not exist? Corners and discontinuities. Forget that. So anyway, just a quick little rundown of that.